Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all the students. And this is again DMM1523 or DRM1213, Engineering Materials, Section 1, MO1 and RM01. And now we are moving to Chapter 2, which is Material Structure and Bonding. So as for the chapter objectives, number 1, it's explained and discuss the atomic structure and bonding. Number 2, understand the relationship between crystal structure of metals and its atom arrangement. Number 3, you should be able to identify and differentiate the imperfection and defects in crystal structures. So as for the lesson objectives, at the end of the semester, students should be able to analyze and illustrate the materials, atomic bonding and crystal structure. For topic content, we are going to look at on the atomic structure and bonding. Number 2, we are going to look at on the crystal structure, such as BCC, FCC, HCP, atom arrangement. And then last but not least, we are going to look at on the imperfection as well as defects in crystal structure. Now, as for topic number 1, the atomic structure and bonding. So what is atomic structure? In atom, it consists of a nucleus plus electron. As you can see here, this one is actually the basic structure of basic structure unit for all engineering materials. Yeah, there's a nucleus, then also electrons there. And then in atomic structures, there's electrovalence that you need to know. Electrovalence or valence electrons are the electrons that occupy the outermost field shell. These electrons are extremely important as they participate in the bonding between atoms to form atomic and molecular aggregates. Most of the electrical, chemical, mechanical and thermal properties of the atoms of solid are based on this electron valence electrons. For example, by taking a carbon with atomic number of 6, you see the arrangement, the first shell, it got 2 followed by 2, the second shell, and then the outer part which is 2. So the electron valence is the most outer part of the shell itself, which is 2. The other materials, the other types of materials have their own valence electron as stated in this table. So you can see it from hydrogen, helium, lithium, boron, and so on and so forth until krypton. You can see the numbers at the outer shell part represent the valence electron for each types of materials. And if you refer to the periodic table here, to the left, meaning electropositive elements, which means the materials itself ready to give up electrons to become positive ion. And to the right, the materials represent as the electronegative elements, whereby they are ready to acquire or receive electrons to become negative ions. And things that you know and need to know in atomic structure and bonding is electronegativity. Electronegativity is referred to the tendency of an atom of a given chemical element to attract shared electrons when forming a chemical bond. And an atom's electronegativity is affected by both its atomic number and the distance at which its valence electron resides from the charged nucleus. If you look at this periodic table here, to the left is smaller electronegativity and to the right larger electronegativity. So the value of electronegativity ranges from 0.9 to 4.1, and it differs from different types of materials. So the larger the electronegativity means the more tendency it is to acquire more electrons. There are several types of, in major, there are two types of bonding in atomic structure. Number one is primary atomic bonds, and second one is secondary bonding. For primary atomic bonding, it can be classified into three types, which is ionic bonding, number two, metallic bonding, or covalent bonding. Okay, now let's look at number one, which is ionic bonding. Ionic bonding is a type of chemical bonding that involves the electrostatic attraction between oppositely charged ion or between two atoms with sharply different electronegativities, and is the primary interaction occurring in ionic compounds. For example, if you take natrium chloride here, you see this is natrium and this one is chloride. Natrium is positive cation, positive is cation, and chloride is anion, so it will attract each other. This is a ionic bonding with, you see, with chemical types of bonding. And then again, same to this part, because it is the same periodic table actually. So if you refer to this one, to the left would be more tendency to give up electrons, and to the right, tendency to acquire or to receive more electrons. As for the ionic material properties, ionic bonding actually very hard because particles are not easily slide past another, and there are good insulators because there are no free electrons or ions. And then number three, ionic bonding are brittle and tend to cleave rather than deform because bonds are strong. Number four, it has high melting points because ionic bonds are relatively strong. And number five is that some are transparent because their electrons are not moving from atom to atom and less likely to interact with light photons. Number two is covalent bonding. Covalent bonding is a chemical bonding as well that involves the sharing of electron pairs between atoms. These electron pairs are known as shared pairs or bonding pairs, and the stable balance of attractive and repulsive forces between atoms when they share electrons is known as covalent bonding. Okay, for example, CH4 here, which is methane gas. Carbon stays in the middle, and it shares four hydrogen atoms at the outer shell of its circle there. So that is known as covalent bonding. Now let's move on to another types of primary bonding, which is metallic bonding. Metallic bonding is a types of chemical bonding that arises from electrostatic attractive force between conduction electrons and positively charged metal ions. It may be described as the sharing of free electrons among a structure or positively charged ions. Let's see the example here. Yeah, so this is an example. If you look at here, there's a sea of electrons here because they do not belong to any one atoms, but they are part of the whole metal crystal. So that is metallic bonding. Metallic bonding is known as non-valence electrons and atomic nuclei from iron cores, which possess a net positive charge equal in magnitude to the total valence electron charge per atom. These types of bonding might be strong or might be weak depending on types of materials that is going to be used. And as for the properties for metallic bonding includes good ductility, good electrical conductivity, lustrous and malleable. And this one is another examples of metallic bonding. So you can see there are positive ion in core and valent electrons, a form of electron charge clouds. So there's no ions belongs to one and another. They are uniformly distributed. So move on to second types of bonding, which is secondary bonding. Secondary bonding are not bonds with valence electron being shared or donated. They are usually formed when uneven charge distribution occurs, creating what is known as a dipole. Dipole represent the total charge is zero, but there is slightly more positive or negative charge on one end of the atom than on the other. Or it can be a combination of a bonding. So that is known as secondary bonding as well, which always occurs in polymers. Other example, you can see hydrochloride and also polymer. Okay, so in general, there's a positive and negative together. This is the primary bonding, and then primary with primary combining with each other, turning into secondary bonding. Same goes to HCl and so on, so forth. So in summary, we can say that ceramic is ionic and covalent bonding with large bond energy. Metals consist of metallic bonding with variable bond energy depending on types of materials. Last but not least is polymers. It has covalent and secondary bonding. Well, its directional properties. It has directional properties and dominated by the secondary bonding. Yeah. Okay. Now let's move on to crystal structure in metals. In metals, we can say that there are two types of structures, crystal structures that can be found, which is crystalline and non-crystalline. For crystalline, is also known as amorphous. For crystalline, normally the atoms being arranged in 3D. And examples of materials is like metals, ceramic, and some polymers. For amorphous or non-crystalline materials, the atoms have no periodic packing, which means that it doesn't have specific arrangement for amorphous, and it is much more complex. It occurs because of rapid cooling, normally due to rapid cooling. Let's take an example for crystalline solids, which is quartz crystal. This one can be either single crystal or polycrystal. Its properties are related to orientation and depend on the crystal axis. It's either anisotrophic or isotrophic, and crystal become liquids at specific temperature. If you look at this profile here, as the temperature increases, below melting temperature, obviously it will stay in solid, which is in crystal, either single crystal or polycrystal. And then once it is melted, then it will change straight away into liquid. As compared to amorphous or non-crystalline materials, if you refer to this profile, below melting point, it is in solid solid condition, solid properties, and once heat being introduced to the materials, it starts to soften before it change into 100% liquid. So the most simple example that you can see is wax. Yeah. So whenever you heat the wax, it will soften first before it turn into liquid. Okay, now let's see the arrangement in crystal structure. You can see in crystal structure, there are three types of arrangement, which is BCC, FCC, CPH. Okay, the arrangement of the atoms is called crystalline structure, and it has a space lattice and unit cell. Space lattice is a 3D array point coinciding with atoms' position, and unit cell, smallest repetitive volume, which contains the complete lattice pattern of a crystal. So basically, this one, unit cell coming from the space lattice here. And this is the lattice parameter. Things that you need to know is A, B, and C, as well as its angles here, alpha, beta, and gamma. And this is the crystal system, or sometimes you may come across with Bravais terms, Bravais lattice. Well, Bravais lattice refers to the 14 different 3D configuration which atoms can be arranged in crystals. The smallest group of symmetrical aligned atoms which can be repeated in an array to make up the entire crystal. So this is called a unit cell. There are several ways to describe lattice. The most fundamental description is known as Bravais lattice. In word, Bravais lattice is an array of discrete points with an arrangement and orientation that look exactly the same from any of the discrete points. That is, the lattice points are distinguishable from one another. Those Bravais lattice can refer to one of the 14 different types of unit cell that a crystal structure can be made up of. So out of 14 types of Bravais lattice, some 7 types of Bravais lattice in 3D space are listed in here, and the other 4 are the basic types of unit cell, which is simple cubic, BCC, FCC, and C and HCP. This table listed the lattice type relationship and figure showing unit cell geometry for 7 crystal system. Actually, this one can be also obtained from your reference book that I have been suggested to you from previous lecture. So we can refer it to that table as well. And same goes to this one. Okay, some people do question, why do different types of metal have different properties? Yes, obviously it depends on the structure, which means the arrangements of the atom. For example, if the atoms are very packed and dense, obviously it will become much more strong and hard as compared to those who have a lesser atoms with loose atomic bonding. Obviously it will become softer as compared to the materials mentioned just now. So it depends on types of materials and the arrangement of the atoms itself, which finally will affect the final behavior of that material. Like I mentioned just now, there are 3 types of metallic crystal structures that you are going to learn, which is BCC, FCC, and HCP. HCP stands for hexagonal close packed. Okay. Now, the parameters already introduced to you, which is A, B, and C. Just now, A, B, C, which is equals to 0.287 Newton meter, and the cubic side of the unit cell of BCC ion at room temperature is this one. If unit cells of pure ion are lined up side by side in 1 mm, there will be 1 mm times with 1 unit cell divided by 0.287 times nanometer times 10 power of negative 6 mm of a nanometer equals to 3.48 times 10 power of 6 unit cells. So this is how you calculate unit cells, unit cell for BCC. Okay, in crystal structure, you need to know on how to calculate the number of atoms in that unit cell. So formula, you can use this one. N equals to Ni plus Nf over 2 plus Nc over 8. Ni represent for interior atoms, the atoms that stays inside of that unit cell, and F, the number of face atoms, the one that stays at the face of each side of the cell, and then Nc, the atoms at the number of corners atom, the one that stays at the corners of that unit cell. So for example, for this case, this one is simple cubic. Well, normally simple cubic is very low, very rare due to low packing density. Normally the one that being used is like BCC, FCC, or HCP. Okay, so let's try to calculate number of atom for simple cubic here. And I equals to 0 because there's no middle or interior atoms in that unit cell. So 0 plus number of atom at the face. There's no atom staying at the face of the cell, so 0 over 2 plus number of atoms at the corner. Yeah, there's atoms at the corner, which is 1, 2, 3, 4, 5, 6, 7, 8. 8 over 8 sides. Then altogether equals to 1. So for simple cubic, number of atom equals to 1. What happens to BCC? Okay, before that, we'll see the calculation for number of atom for BCC afterwards. But before that, other than number of atoms, things that you need to know in crystal structure is atomic packing factor, which is APF, with the formula of equals to volume of atoms in unit cell divided by volume of unit cell. Volume of atom in unit cell divided by volume of unit cell. Volume of unit cell. Okay. For example, for BCC, okay. So how do we calculate this one? APF for volume of unit of cell here. This one, volume for cubic, is very simple, which is A power of 3. Yeah. A times A, A times A times A. So you got A power of 3. That is volume of unit cell. For volume of atoms in unit cell, first of all, this one, the spheres there. You need to know, you need to remember the formula for sphere. Formula volume for sphere is equals to 4 over 3 pi r power of 3. R here equals to, luckily you got the value of R here. R equals to 0.5A. So substitute into value of R here. So this is the volume per atom. And then we know that the number of atom for BCC is no, this is not BCC. Simple cubic is 1. So times 1. Then calculate the value. You will get the value of 0.52 for simple cubic. This is value for APF, atomic packing factor. Okay, now move on to BCC, body-centered cubic. How many atoms? How do we calculate the value of atoms in BCC? So first of all, n equals to 1 plus 1 refers to interior atom in the structure, 1 only, plus face, a number of atom at the face of this cube. There's no atoms there, so 0 divided by 2 plus corner atoms. Yeah, there's a corner atom, 1 2 3 4 5 6 7 8 at the back, divided by 8, and altogether equals to 2 atoms per unit cell for BCC. So now let's look at the how to calculate the APF, atomic packing factor, for BCC. Okay, however, first of all, the question asks you to find the relation between radius and also A here. Okay, the first thing that we have this cube, okay, and this is the A, and that one is a radius for spheres there. So A, this one is A, so over there you will get cert A, cert 2A, cert 2A, and then this side you'll get cert 3A. Okay, like this. So now it's proven. Closed pack directions length equals to, for R equals to cert 3A. So radius will get, for the value of radius, equals to cert 3A over 4. Now, once you get this value of radius, then you can calculate the value of APF here. APF, again, the formula is that volume of atom in unit cell divided by volume of unit cell. The volume, formula for volume is A times A n times A. So you'll get A power of 3. And then this is for volume. After that, you need to calculate the volume for atom first. Volume for atom, remember formula for spheres, 4 over 3 pi r square, pi r cube. So radius cube, you get the r here, and then substitute into the value r here. So that's why you get cert 3A over 4 power of 3, and then you need to times with 2, because for BCC it has 2 atomic numbers. Okay, and finally you will get the value of APF for BCC, which is equals to 0.68. Okay, now let's move on to other types of crystal structure, which is FCC. So again, the same formula, and equal to let's look at the internal atoms in the structure. If no, then equals to 0, plus surface atoms. Yeah, 6, 1 2 3 4 5 6. Okay, 6 divided by 2, plus at the corners 8 divided by 8. Then altogether you get 4 atoms per unit cell for FCC. Okay, so same steps as in BCC, whereby you need to find the value of R first before you calculate the value of APF. Okay, so now you get this structure, and then notice that this is the length is always A here, because the same cubic. Then from your calculation, all right, which one? Sorry. Okay, I think I'd better to refer to this graph, because it is much more clearer here. So how do we get the this one? How do we get this one? The interaction between cert A, cert 2A equals to 4R, because this length actually 4R, but we do only need to find this one in order to get this relation. So we know the length is A, A times A times A, A times A times A, right? Okay, so this one A, this one A, so A square, A square, A square plus A square cert equals to cert 2A for this length. So finally, you get this relation. Cert 2A equals to 4R. 4R is given. You just need to find cert 2A only. Yeah. Okay, from there, you know closed pack directions, length equals to 4R or equals to cert 2A. Number of atom, which is 4, and then start to calculate the value of APF, which is this one is volume, then this one is the volume for atom. Remember to substitute the value of radius into this formula, and then finally times with 4 because it has 4 atoms per unit cell. And finally, you'll get the value of APF for FCC equals to 0.74. And then the last but not least is for HCP, which is hexagonal closed packed structure. This one is a little bit complex because of its structure. However, the step is the same. So let's look at how can we calculate atoms, its number of atoms for HCP. Okay, and equal to 3. 3 meaning those in the middle here, 1, 2, 3 times, well, the calculation for HCP is slightly different than those in the previous crystal structure, yeah. Okay, and then 2 times half. Okay, this one means if you refer to the upper part and the bottom part here, you'll get a atom, half of the atom facing at the face of the cell, one half which is at the half at the part at the upper part, and half is at the lower part. So you get 2 there. That's why half times 2 plus at the corner atoms. Corner atoms, there are 6. There are 12 of it. 12, which is at the upper part and the bottom part, and it has 6 corners. So that's why 6 corners. That's why we need to divide by 6 corners there, and altogether you'll get the total numbers of 6 atoms per unit cell for HCP. So that's how you calculate the value of end. Okay. Now let's look at this example. The question asks you to calculate the volume of zinc crystal structure in unit cell by using the following data. Pure zinc has the HCP crystal structure with lattice constant A equals to 0.2665 nanometer, and C, A this one, okay, C this one, C equals to 0.4947 Newton meter. The ratio of the height C to its vessel called vessel A called C over A ratio, okay, which is equals to 1.633. Okay, so now it asks you to find the volume of zinc crystal structure by using this one. Okay, so the first step is that you need to calculate this one, the area for this one. Okay, sorry, because the answer is already here. Okay, so from figure C there, you just need to calculate the area for triangle ABC just now. Area ABC. So you have A for triangle, half times width times height, which is half A times A sine 60 degree. After that, from figure B there, you need to times with total area in HCP, which is 6 units here, 1, 2, 3, 4, 5, 6. So just time with 6, you'll get this one. And then finally for the volume, once you get the total area, then you just need to times with height, which is C here. C So this is the value for C. Then just substitute all the information there. You will get the volume of zinc HCP unit cell equals to 0.0913 nm cube. So again, you just need to calculate it step by step. I repeat, you just need to calculate the area for this right angle. After that, you need to multiply with 6 because of the 6 section there. After that, just time with height or C value here for volume. Okay, in summary, the comparison for FCC, HCP, and BCC crystal structures are stated as follows. You can see the atomic position for BCC, FCC, and HCP are slightly different. And then for the APF is BCC is different, but FCC and HCP is the same. Example of application for BCCs like introduction, iron, tungsten, chromium, molybdenum, vanadium. FCC, aluminum, copper, lead, nickel, and iron. HCP, yeah, you can read it on your own for these types of comparison. Okay, another part that you need to know is the density of the crystal structure, and this is the formula for crystal structure. Formula for density, theoretical density for crystal structure. Rho equals to mass of atoms in unit cell divided by total volume of unit cell. Mass of unit atom cell, Na, divided by total volume of unit cell, which is BC and A. So each of it represent N is for number of atoms per unit cell, A atomic weight, VC volume of unit cell, Na stands for Avogadro's number, whereby this one is a specific number. Okay, so now let's calculate the value of theoretical density for BCC. Okay, so this one we get it from our previous calculation, the relation between A and also radius there, but before this we use the value of radius, but in this case you just need to interpolate a little bit just to get the value of A, which is equals to 0.2887 nm. Okay, R value is given to you, so you can just substitute into the formula. P equals to A is the for unit for volume per unit cell is A3, always A3. Substitute value of A into this one times with Avogadro's number just now. Okay, and then for the upper part is that the upper part is mass of atom in unit cell. Mass A weight is given, and then you just need to times with atoms per unit cell because BCC has two numbers of atoms. So from there, substitute the just calculate it, and then you'll get the value of theoretical density equals to 7.18 gram per centimeter cube, or for actual density equals to 7.19 gram per centimeter cubic, or 7.2 gram per centimeter cubic. All right, and you see in general the density for different types of materials are different. For example, density for metal is much more higher than ceramics, and ceramics is much more higher than polymers. The reason is that for metal, it has a metallic bond, which is very close packed, normally with large atomic masses. And for ceramic, it has less dense packing, often lighter elements. Polymer, low pack density, normally amorphous with light element like carbon, hydrogen, oxygen. whereas composite have intermediate values. So that's why you see different types of materials has different properties. Yeah. Well, density is include one of the properties for the materials, and you may refer to this table for the differences or material classification for density. Yeah. Now let's move on to single crystal versus polycrystal. For single crystal, properties vary with direction, which is anisotropic. For polycrystal, properties may or may not vary with direction. However, if the grains are randomly oriented, it is called isotrophic. And if the grains are textured, it is called anisotrophic. And there's also another term, which is polymorphism. Polymorphism instead two or more distinct crystal structures for the same materials. It exists, for example, by taking a titanium. In titanium, there's different types of crystal structure exist in it, like alpha, beta, alpha and beta titanium. And same goes to carbon. There's a diamond and also graphite in it. So that is a polymorphism. Okay, that will be all for single and polycrystal as well as polymorphism. Now the last topics for this lecture is on imperfection and defects in crystal structure. The properties of materials are a function of their bonding structure, crystal structure, and imperfection, which is defects. So in this part, we are going to look at on imperfection. Okay, I want to show you this slide actually. There are different types of imperfection that might be occurring in crystal structure. For example, point defects, line defects, and area defects. Point defects, it can be either vacancy atoms, interstitial, or substitutional. Whereas for line defect is normally known as dislocation. Area defects is known as break boundaries. Okay, let's look at one by one. For point defect, let's look at for this one first. For point defects, okay, which is vacancies. Vacancies, you can see there. There's a vacant, vacant and this atomic arrangement. This one might be occurred due to distortion of plane. Same goes to self-interstitial. You see, there's a self-interstitial there, whereby extra atom position between atomic sites. This one, point defects in metal, and point defects in ceramic is the same. Yeah, it's either vacancy or interstitial. Okay, vacancies exist in ceramic for both cations and anions. For interstitial, exist for cations only. Interstitials are not normally observed for anions because anions are large relative to the interstitial sites. You can refer to this figure here for cation interstitial, cation vacancy, and anion vacancy. And you can compare the size of it. Now, let's look at the imperfection in ceramics. Normally, imperfection in ceramics is that the charge balance must be maintained when the impurities are present. For example, natrium chloride, this one without impurities, and then suddenly there's a calcium impurities. This calcium will attract natrium, and therefore, if you look at the overall atoms, there's a cation vacancy there because it's already interact with interact with natrium with calcium there. Okay, another one is substitutional anion impurity. this one without impurity, and this one with O2 impurity. You see O2 will attract chloride towards it, and suddenly we can see in this figure there's an ion vacancy there. This one is with impurity. Okay, the second one is point defects. It occurs due to chain packing errors and impurities such as chain ends and side chain ends. Example of dislocations, it can this one is dislocation. Okay, point defects. Okay, this one is line defects. It happens due to slip between crystal planes results when dislocations move. It produces permanent deformation, which is a plastic deformation. So you see this figure. This one, this is the original parts. This one after it dislocated. So this one. Okay, that will be happen to that material. Or else you can refer to this figure here. What happens to the materials starting from figure A, B, and C. So this is considered as plastic deformation, whereby plastic deformation meaning that it doesn't show its original form. It's changed totally, so it can come back to its original form. Okay, continuation for line defects or dislocation. Types of dislocation includes edge, screw, or it can be combination of edge and screw. Later on, we'll see the figure for edge and screw dislocation. And it normally occurs during solidification, plastic deformation, or during rapid coolings. Because of the during rapid cooling, there's a thermal. It will contain thermal heat in there, and then it will occur thermal stresses inside the materials. That one will happen during rapid cooling. Okay, so figure A showing a edge location, edge dislocation. This one, and then screw dislocation. Okay, or this one. I think this one much more clearer to you. So you can see this is the edge location. It moves perpendicular, and for screw dislocation, it moves like it tilts a little bit. So look at this one. Look at its direction of dislocation here. It is different than edge dislocation. Okay, or this one. This is also how it moves, and finally creating edge dislocation. Other than that, the imperfection in solids. Normally, you can see these types of imperfection by using microscope. Okay. Area of defects, grain boundaries, regions between crystals, occurs normally regions between crystals like this one. This is the grain boundary. Okay. So as a summary, point, line, and area defects does exist in solids. The number and types of defects can be varied and controlled. For example, by using a temperature and so on and so forth. After that, defects may be desirable or undesirable. It depends on the types of product that we are going to produce. Well, you see, there are continuation for these topics in your program, like design, solid mechanics, and so on and so forth. So that would be a continuation for this topic or for this subject. So thank you very much for your kind attention. this would be a very long lecture for today, and I hope you could be able to understand all the lecture. But anyhow, if you still have problem in understanding the topics for today, you may always contact me through group WhatsApp or Google Classroom, or email. Is up to you, and I'll come back to you as soon as possible. And thank you very much. That will be all for chapter 2. By right, we shall be having a quizzes in the next class. With that, thank you very much. See you again in the next class. Okay, Assalamualaikum warahmatullahi wabarakatuh, and good day. Bye.